where kind of things people are looking at. And so I want to title this lecture as the geometrization of field theory. So a lot of things we learnt in this course, like the Higgs mechanism and enhancement of gauge symmetry, things picking up masses, all these things in a very simple field theory, they actually can be given a geometric meaning, and that would not be a big deal, because that would correspond to choosing a field theory with a particular kind of potential. But the thing is that that field theory is very natural, they appear naturally in string theory. And so all these geometric pictures which I am talking about is something one gets by doing string theory and trying to understand field theories which arise in those contexts. Even though string theory is a theory of quantum gravity, that is not what I am looking at. I am just thinking of it as something which gives you a class of field theories, okay. And the field theories are quite nice, but before I do that, there is one important classical field theory which we have not discussed in this course. Does anybody know which one? A very famous general theory of relativity is a very famous classical field theory which we have not discussed in this course. One of the reasons is that there are other courses in this place for that topic, but I just want to mention one way of thinking about general theory of relativity which naturally fits into the scheme of things of this course, and that is actually very anti-geometric. In some sense I would say anti-Einstein, because really what Einstein did was to geometrize gravity, okay. So even though it is kind of ironic that today's lecture is geometrization of field theory, I am going to give you one non-geometric way of looking at general theory of relativity, and so at least let me not write it in this part of the board, I go there and write it out here. So if you recall, what we did was we took some global symmetries and made it local, and all the examples we looked at were internal symmetries which did not act on space time, okay. So but so we could just go ahead and say, suppose we consider Lorentz symmetries or the Lorentz group. Now this is something which acts on space time, and if you ask what is the meaning of making this local, it means at every point you make a different rotation or a boost. So it's so the thing is that so you can see that this actually, once you make it local, it just corresponds to general coordinate transformations. So even things like translations fit into that. So the whole Poincaré group becomes subsumed by this, because they are examples of special this thing. So the first thing is to ask how things will transform. So for instance, already we saw, if you take a vector field under general coordinate transformations, it should transform. So A prime let me put even this argument. So you write something like this: A mu of x prime equal to. So this should be the transformation of a vector field. So you can define tensors in saying, so this is really the Jacobian of the coordinate transformation change, right. So what you are doing is you are saying x prime of mu is just some x prime of these coordinates. That is the general coordinate transformation. And obviously you can see things like you can ask what happens if I take a derivative of this, how does it transform? Does it transform nicely? Fun exercise is to ask how f mu nu transforms. Given this transformation, you take a derivative, so you work out f prime nu, does it transform nicely, okay. So, what you will find is in general many things will not transform nicely, and you need to introduce a connection, and the connection in this case is will turn out to be the metric. Okay. And so you can go ahead and you can make, so then you can come up with rules which says that there is this covariant derivative which makes things transform nicely. So you will so you will introduce, so this is the analog of a mu, which we introduced for internal symmetries, and so you will have some notion of a covariant derivative. And the measure will look something like this, minus det g. Okay, so this is a nice measure. So you can make this, and you can also ask, so let us say we define some covariant derivative like this, and you can ask this acting on something will give you the analog of field strength, right. So I am being very schematic out here. This object will turn out to be the curvature tensor. Okay. So there is something called the tetrad formulation of GR or general relativity, where it fits much closely to what I am writing out here, much more closely, and so this is one way of looking at GR, but this is not the way even I would teach a general relativity course. I would start from the the geometrization of I would say of gravity due to Einstein. Okay, that is a different thing, but it is still useful to think of it this dual viewpoint. Okay. So coming back to geometrization of field theory, so the example we will choose is we will consider the field theory in p plus 1 dimensions. Okay. And I should give you the spectrum. Spectrum is a gauge field, a mu. So mu runs from 0, 1 to p. That is a gauge field. So for starters, we will just think of this as a u1 gauge. No, let us take it to be a un, or this is a non-abelian gauge field. So I was using script a or whatever, right, for that. So let us leave it that way. And suppose it also has bunch of adjoint valued scalars, and there are 9 minus p of them. So let us just call these phi a, where a runs from. So what I will do is, since there are 9 minus p of them, I will just label them as p plus 1 to, instead of calling them 1 to 9 minus p, I will just write it as p plus 1, p plus 2. Okay. So this is the spectrum or the fields. Okay. And we need to give an action or a Lagrangian for this thing. So the Lagrangian for this gauge field, so we will write the simplest guy we can think, 2 derivative 1. So it would be minus half trace in the fundamental of say f mu nu, and then so here there is no this trace is in the adjoint, obviously, because these are adjoint valued things. So that is just d mu covariant derivative of phi a okay. So, this is the first things we would have written, and we could put let me put a coupling, let us call it a G square Yang-Mills coupling, and plus how do I write this, minus u of phi. Okay, this is what we will write. Now, I need to give you u of phi. By the way, we can also see that this spectrum can be obtained by the dimensional reduction starting from, we have seen this one before. So, this also, this can be understood as a dimensional reduction of pure gauge theory, pure Yang-Mills in 9 plus 1 dimensions, and then you will see that these fields are basically what would have been in 10 dimensions gauge fields, they give you adjoint valued scalar. Okay. Is this clear, this the spectrum? So, the u of phi is again like we did we had discussed will be just so how does yeah, so it will be something like phi a, phi b, take its commutator, whole square and a trace. Okay. So, this is potential is somewhat different from what we looked at. We were looking at things like lambda phi 4 and those kind of potentials. This is very different. Okay. And but this is perfectly good potential, and this is natural in this theory. Okay. So, now we want to let us go ahead and try to analyze the ground states of this theory. So, the ground state would be obviously when things so we could look at a situation where all the gauge fields are 0 like we did even in the other case, and the fields are also time independent. So, these just become matrices. Okay. So, to analyze the ground state, so the vacuum okay. So, we will just say a mu is 0 and phi a are constant matrices. Okay. So, it comes down to just saying that this thing the square is in the wrong place. So, the phi a is a constant matrices, and you can convince yourself that this thing, the lowest smallest value it could get is 0. So, when would that happen? When phi a and phi b commute. So, the vacuum configuration, so the lowest energy or vacuum when okay. Is this clear? And what we will do is we will think of, since these are adjoint value objects, we can think of them as n by n matrices, which is now so if you in the fundamental representation. So, even here we could make this, let us make it fundamental, then should say, so we have not chosen a group, have we? So, let us choose the group to be SUN. Okay. I will change it to UN pretty soon. So, but since we discussed SUN, so we will just, so in the fundamental, so these phi's, phi A's are n by n matrices. Okay. And if we want all of them to commute, the simplest solution is that they all be diagonal matrices. Okay. So, star is solved if all the phi A are diagonal. Okay. So, let me just remind, let us before we proceed, what is the difference between SUN and UN in terms of Lie algebras is that the basis for SUN is traceless Hermitian matrices, while the basis for UN is you just get rid of the trace condition. That is related to the fact that the group there is no determinant condition. Okay. So, out here, so similarly here, so I think of phi A is not as traceless matrices, but they can, I will permit them to have trace. Okay. So, let us just take n equal to 2, then you can see that I could write phi A would be V A1 V A2 0 0. Okay. So, now what we see here is that there is a whole set of vacua specified by how many numbers there are. A runs over 9 minus p. So, there are 2 into, so implies that we have 2 into 9 minus p parameters that describe the vacuum. Okay. So, is this clear? These are the numbers, for all of them the energy is 0. So, they are all equal. So, it is very there is high degeneracy, in fact it is parameterized by this thing. You can see very easily that if for for UN this just 2 becomes n. Okay, but I will keep using SU2 as my example, the generalization will be straightforward. Okay. But now we can ask what does this mean. Okay. So, we can go ahead and do what we did in our field theory other examples. We asked what we go ahead and put fluctuations and ask. So, here we what was the thing we did, a mu is 0. So, you any a mu you turn on is a fluctuation, but to this I can add so I can add fluctuations which shift this. Obviously, those are massless guys, but then I can turn on off diagonal elements, but we have to still preserve the fact that it is Hermitian. So, really you have all these parameters which you can turn on, and the question is what happens. Okay. So, there will be obviously when, so let us first look at the case 1, which is all the VA1 equal to VA2 are all 0. Okay. So, this is analogous to the unbroken thing which we would have had, where all the fields were 0. Okay. So, we will so in this phase we will call it a phase, all gauge excitations are massless. Okay. they are massless, and yeah, and there is an unbroken U2 or SU2 symmetry. Okay, I will keep going back and forth. SU2 symmetry. Let's call it U2 only. Very easy to see. I mean, there is nothing. So you work it out to quadratic order, and you can see that. Okay. So this is usually called the Coulomb phase. The nomenclature is as follows, is that in the so a Coulomb phase is where the gauge fields are massless and they can propagate. If there is a Higgs mechanism and something becomes massive, those things because they are massive, they will not be propagating degrees of freedom. So in some sense, from condensed matter physics, when you take in the superconductor, in the Coulomb phase is where you have conduction. If there is a mass, then there won't be. Okay. So when the U1 becomes massive, so this is called a Coulomb phase. Case 2 is when VA1 or VA2 or everything, some of the VAs are non-zero. Okay. So in particular, let's choose phi A. Let's choose a kind of, I mean, this is just only an example of this kind. I choose the same this thing, I make it traceless by hand. I am choosing a subspace in this thing where it is traceless. They need not be the same for each one of these things, and or even better, let us just say this is only for one of them, say for A equal to P plus 1 and 0 for others. This all other and it is phi A equal to 0 otherwise. So we will just okay. Again, this is exactly like what happened in the Prasad Sommerfeld case, where you said that the only thing which you remembered there was the wave things took and the potential could have been forgotten, but this is here there is exactly that is what is happening, the potential goes to 0, there is no need to take any limit once you put this thing. But now you look at fluctuations, what you will see is that this thing breaks SU2 to U1. This is the one we have looked at, but the U2 has an extra U1 that will be unbroken. Okay, and the mass of the W, so there will be W plus and W minus, right? There will be two massive guys, and the mass of the W, so I will just call them mass of W plus minus, will be among other things proportional to V P plus 1, this number. There will be G factors, all those things, but this is the mass, right. So there we have the Higgs mechanism at work, and so it is kind of fairly straightforward, but now is where the geometric picture comes, where you interpret these things somewhat differently, and so I have to explain. So what I will do for you is explain where this kind of spectrum comes. So in string theory there are extended objects, okay. There are solitons that are extended objects. Okay. So idea of so most of the solitons, like for instance we saw the king soliton, that was like a particle, okay, and if you look at its time evolution in space time, it is like a line, okay. But you could have, there could be so let us draw the space picture. So there is always a time, so this is what we would have called a particle, but there could be something else which is extended in one direction. I am drawing a curve, but let me draw it as a straight line, and what would you call something like this? You would call it a string, okay. If you add time, it becomes like a sheet, and you could have something which has two such directions. You would call this a membrane, okay. And in general there can be an object which carries which is p plus 1, this is p dimensional, so I can't draw that picture anymore. So you just call this a p brane. So in that nomenclature, particle would be p equal to 0, this would be p equal to 1, p equal to 2, okay. So we are not looking at the string theory equations of motion or anything, but I am just saying that there is this soliton. But first thing you can see is that existence of so a p brane, it breaks translation invariance. So suppose you have a particle in some space, you have to give me its position, it breaks translation in all directions. But if you have a string, along the direction of the string translation invariance is not broken, but translation is broken in the perpendicular direction. So in a p brane you do not break translation invariance in p plus 1 dimensions, and you break in 9 minus p. So yeah, I should mention that these are objects living in 9 plus 1 dimensions. So it breaks translation invariance okay. So for pictures I will use this and generalize, because it gives me some this thing, translation invariance in 9 minus p directions. Okay. In other words, so let us say that we are in 10 dimensional space x m, where m goes from 0 to 9, okay, and let us assume that this brane is along p brane is specified. So we just have simple, what I have in mind is something like a flat sheet, you know, p brane is given by saying that x in A equal to some constants for A equal to p plus 1 to 9. Notice that the breaking I am doing is exactly like what had happened earlier, okay. So this is what is going on. So let us go back to the case of the king soliton. King soliton was in 1 plus 1 dimension, it broke translation invariance in space, right. So then we saw that there was exactly one 0 mode, and if you want to do quantum mechanics of that soliton, we have to quantize that 0 mode, there would be one this thing. So the quantum soliton would be saying you treat that position as a coordinate in quantum mechanical problem. But let us take something like a string and ask, so obviously there should be, this is breaking translation invariance in all those directions, so we should have 0 modes, okay. But the interest, so the thing is here unlike the kink, what will happen is that this thing will become a field on the soliton, and the way to see that is, so let me draw a string. There are many dimensions, but since my board is just 2 dimensional, so it is preserving translation out here, but it is breaking along this direction. But now the thing is, if I am interested in small fluctuations, I can replace this by something like this, So this, let us call this direction sigma. So I can discuss fluctuations of this thing. So the mode here which corresponds to I mean you might think there is one mode obviously which means translate everything equally, but why should I do that? I can do it at every point, I can make it different. So the 0 mode is actually a field. So the 0 mode, okay. So in this, if it were a particle, it will still be a function of time, right? I mean I can think of some time dependent kind of solution, and then this, in that same sense the 0 mode here can be elevated to a field. It is a one dimensional field, rather 1 plus 1 dimensional field. So let us call this thing, I will call that thing phi, and it will be a function of sigma and of course time. Okay. And how many of them are there? Because this is p equal to 1, there are so many, I mean because I am in a board I could draw only one of them, but there are as many of them as this thing. Okay. So I get a single scalar field for everything. It is very clear now, for a p brane I will end up getting something which is a p plus 1 dimensional field, scalar field. Okay. So this sort of tells you that the claim is that the 0 modes or the light fluctuations of a p brane are given by 9 minus p scalar fields, okay, in p plus 1 dimensions. Okay. And then you can ask, so the point is that it is only the yeah. No, it is the transverse directions, right? Directions along the, so along the thing the translation is not broken. So in p plus 1 dimension it is not broken. Okay. So this is just Goldstone's theorem, it does not need any glorified stuff, you know, it is just Goldstone's theorem being applied out here. Okay. So I am just saying that the low energy modes will be that of a field. Okay. Even if you are interested in so coming back to the King soliton, even there x0 which is not a function of t is the exact solution, but if you want to do dynamics of that object, you want to quantize that object, what you would do is you say let us make it a function of t, assume it is a slowly varying function of t, and then you will get an effective, you can plug it into your action and you will get an effective thing which would give you the quantum mechanics of that 0 mode. Okay. You will see that x0 plus vt, so that will also go away, but then the next derivative will come. So it is a nice exercise to go take your kink soliton solution. So and wherever we saw x, we put x minus x naught of time, or call it q of t, so that you feel way more comfortable, and you integrate out, you plug that whatever was the kink action, put it in there, and you will automatically get a kinetic energy term, which of course it will be, it should become 0 when it becomes a constant. So you will see things will work beautifully, you will get some effective action or effective energy function for that thing, which will agree with your intuitive thing. So that is the only thing which one is doing here. So I am doing something similar here to explain to you that the low energy dynamics of this thing is given by this kind of a field. Okay. But you could you know, you need not do that, you could say let us ask what is the thing, let us stick to 2 derivative etc., and you will naturally write, and there are symmetries in the theory, you would write something. Okay. So for instance if you look here, rotation group which would have been SO9 comma 1 is broken up into SO p plus 1 part and cross SO9 minus p. So you will write things which are Lorentz invariant combinations of these phi a's. So you will end up getting phi a's of some sigma alphas and t, where sigmas are the coordinates on this thing. Okay. So we could write some effective action for this scalar field. but this is not what we saw, right. I mean, there was also a gauge field in the spectrum. So that is the surprise. The surprise is that string theory gives a slightly different way of looking at the story. It says that you look, it says, so I mean these objects, I mean it is quite natural to look at these kind of objects, and in the literature for decades people had worked through these things and writing effective actions for this. You could write lots of things which involve these kinds of objects, and but the missing ingredient was that there was a gauge field in the spectrum which comes from string theory. And the way is the claim, because I will not be proving, and I do not think it is proven in a rigorous sense, but there is a lot of evidence for this. The claim is that the low energy dynamics of a p brane of the kind I am talking about is given by the fluctuations of an open string. These are just words, they will not make sense for you, but it will give you pictures. Open string that begin and end on the brane. So let me draw the string again, okay, and so now I will use a different color. Okay, it is something like this, and let us assume it is some directed object, something like this. Okay, so now, so the idea, so this statement implies you should go ahead and quantize a free string. It is very easy to quantize, it is not very hard, and you can ask what is its low energy fluctuations. And if you give me the energy of any string is the following, this is the energy of that string, of a classical string, will be its tension, this is some dimension, its energy per unit length, time its length, plus quantum fluctuations. Okay, but we are discussing the lowest energy thing, so all the other fluctuations you would like to this. So if you give me a string which has length L, its energy will be, the lowest possible energy would be tension into its length. Okay, so now you can see that, so what would be the lightest string you could do? You could think of a string of size going to 0 size. So in other words, that is so there is a mass flux excitation which is called low energy excitation, which so you can go ahead and quantize it, and what you find is you find that it has the string spectrum is infinite dimensional. So there are massive guys, so we forget about those guys, and you find that the lowest configuration has this field, but it also has a gauge field. Okay, so what you find is that there is a phi a, we will use the same notation, sigma of alpha t, but there is a gauge field a mu, this is a abelian gauge field, abelian gauge field. Okay, and this is a very important step, it gives you a completely different field theory than you would have done. Okay, and if you ask what is the action, you could write two derivative, it is exactly what I wrote, but except the potential energy, because it is abelian, there is everything is commutes. So there is no potential energy, no nothing, there is just normal kinetic energy for all these things for a scalar field, that is it, that is what you have. So the question is, how do you get a non-abelian gauge field, and this is where the pictures come, this picture. So this picture right now I drew it for a string, but it is best to think of it as all the p plus 1 dimensions going this way, and this direction is 9 minus p. Okay. So we will call these 9 minus p as the directions transverse to the brane. Okay. So now the question is, how do you construct, how do you get a non-abelian gauge theory? Does not look like you could, and this is how you do it. Consider two parallel d branes. Remember I told you that these are given by this constant, the other one is shifted by some distance. Okay, so let us say they are separated by some distance L. So, what I have in mind is there are two things which are parallel and they are separated this way. And let us take this claim, the low energy dynamics is given by strings which are separated, which begin and end on the brane. But now there are two branes, I can draw many different kinds of strings, and let us look at this thing. So, first thing we know is if you believe that there are two of these things, so we will write, so let us label this fellow 1 1. Okay. So, let us just call this fellow, this comes from, so this fellow will give you a 1, and this will also give you another scalar field 1, it will also give you a gauge field 1. Okay. So, this is just extending whatever observation I had here to the case of two parallel branes. So, now let us but the thing here is if you take this red or pink picture correctly, of course, this came from this guy, this came from something like this, but in principle I can consider strings which begin here and end here. So, we are looking at strings which are directed, so there is a difference between these two. Okay. But these strings are massive because it is separated. Okay. So, that is why they are not there in your spectrum. Okay. So, these are massive. T times L. Okay. Actually, let me not call it L, let me call it V. Okay. T is some tension, whatever that is, there is some intrinsic tension going with that thing. Okay. But now you can ask what happens when they become coincident. The objection that I had is gone. When they are coincident, you will get extra guys. So, let me just so now let me remind myself by saying that this is something coming from a string which is starting at 1 and ending at 1. So, let us keep track of both. So, and this is 2 to 2, 1 to 1, 2 to 2. Okay. But when they are coincident, what you get is you get extra guys, you start getting phi a 1 2, phi a 2 to 1, similarly a mu 1 2, a mu 2 1. They are all vector fields, but they have different labels going with them. Okay. And this happens only when these occur only when they are coincident. When they are not coincident, these become massive, they are not low energy. Okay. But now you can see here there is something neat happening. Instead of keeping so when they are coincident, it makes sense for me to collect 1 2 3 4 as a matrix and think of this 1 1 2 2, this thing has actually the entries in the matrix. So, I just define for you a field phi a which has all these guys. Okay. And similarly here. Okay. And you can see that these are collecting in becoming an adjoint of U2. So, these actually now look like adjoint fields that belong to adjoint of U2, these, and this is of course a connection for U2. Okay. Now, let us assume that this is correct. Okay. So, now we can go back and look at this thing. This so what is happening is when you separated them, these two became massive. Okay. And what was their mass? It is T times V. Go back and compare. We did Higgs mechanism just a little while ago. The Higgs mechanism was precisely that. It tells it and this, that is why I changed L to V. You can identify the separation as with the vacuum expectation value or the number you are putting into in the Higgs phase. The other phase is called the Higgs phase, by the way, I forgot to mention that. So you can see that that is what is going on. So when you take two of these things and you separate them, you are getting a Higgs mechanism. And what are the fields which are becoming massive? It is these guys. So it is really this. So these were precisely this. If you take linear combinations of this, only became W plus and W minus, and there are two unbroken U1s, and what are the gauge fields for them? Those are these two. So U2 broken to U1 square is precisely visible out here. Okay. Now you can ask, how do I get UN gauge theory? It says just take n of them, and now you can see there are many different ways of breaking it. I could take m of them together and separate from the other guys by n minus m. So you would get a breaking of UN to UM times UN minus m. So all sorts of things which you could have done even in your field theory are realized in this picture. Okay. Is this clear? So I am going to conclude with one more example, which we haven't discussed, but will give insight into the ADHM construction of instantons. Okay. And so here we considered branes which are of the same type. Okay. So what we will do is we will consider a system which is which consists of n 0 branes, k 0 branes, and n p branes. Okay. And I will draw a picture now. There are n of these guys, and since this is smaller, I will indicate this by a dot, and there are k of them. Okay. So if you look at it from the viewpoint of this n, you know that what you will get is some UN gauge theory with, sorry, not p equal to 4 with how many? Yeah, so there will be 9 minus p would be 5 scalars. If you look at the same thing with p equal to 0, this would tell you you have, from this one's viewpoint, you will have a UK gauge theory in 1 plus 1 dimension. So it is really quantum mechanical system, but we will still call it gauge theory. So but there will be one gauge field A0 that will behave like a Lagrange multiplier. Okay. UK gauge theory with 9 adjoint valued. So with scalars in adjoint of UN. So I will just write this as n bar, okay, with 9 kk bar scalars. Right, you know that adjoint I can write for UN as n times n bar. That is what I am really doing by writing it as a matrix. So these are by fundamental way of thinking about this, but clearly there are strings which do this. Start from one of these guys and go like this. These will be typically massive, but again if you bring it close enough there will be excitations, you have to consider this thing, but these will be strange things. They will have n possibilities for one end and k possibilities for that other end. Okay. So you end up getting, so these will give you by fundamentals of two kind, n k bar plus k rather n bar k, we can just stick to that kind of notation. Okay. And these are also certain kinds of multipliers. So there will be some scalar, some things coming from this thing. Okay. Now comes the interesting part, what is this object? So now there is one thing which can happen is that when this comes and is living in this thing, so it is dissolving inside that thing and there are these k guys moving. So this is now like a claim. So that will be like the Coulomb phase, what we discussed when they are on top, right. In a Coulomb phase, okay, these k 0 branes behave as k instantons. Okay. So, this is viewing from the viewpoint of these 4 branes. Okay. So, it dissolves in there, it has these 4 dimensions which it can go move around, these are like particles in that thing, and these in fact you can show that these carry instanton number, and there is certain things from string theory which just show exactly that this is indeed true. So, this is just our standard construction which we discussed, but we could have asked it from the viewpoint of this UK gauge theory. Okay. From the viewpoint of this UK gauge theory, you will have a UK gauge theory with these kind of scalars plus additional guys coming from this bifundamental thing. If you look at the details, this is precisely the data which enters the ADHM construction. Of course, they knew nothing about 0 branes, 4 branes, but it gives you a very simple thing. And I also mentioned this gauge theories, that means there is only A0, but A0 has no derivative, we know that. So, A0 behaves like a Lagrange multiplier. So, what you so it imposes some constraints, and if you just look at the ground state condition, you will get some matrix valued conditions which is called the hyperkähler quotient. So, it will be the analog of saying these things commute, there are some rules you get, some things will have to be 0, etc. You get something called the hyperkähler quotient, and actually you get the low energy condition is indeed the ADHM construction. It is truly amazing. Okay. So, with without this geometric picture you would never have thought of this other possibility. Well, that is wrong, because human mind is very good, and 4 big mathematicians thought about it beforehand, but that was like an abstract setting. But I mean, for someone like me, it is sort of straightforward to just go ahead and write the spectrum and write what it is pretty fast. Okay. So, this is what I called as geometrization of field theory, and the real extreme cases are where people have actually pushed things to large classes of examples where you know quite a bit about the theory by asking what is the geometric question, and this is something which you would never have thought of without this kind of a picture. Okay. So, there is this I mean, I think this is really happened in the last 15 years or so, where things have become people have geometrized a lot of these things, and I feel that it gives a nicer way to remember things and understand things also. And but you can see that not all field theories can be realized. You can only realize field theories in this manner which are adjoint or bifundamentals. Okay. So, for instance, extreme cases people have asked, okay, the standard model is SU3 cross SU2 cross U1. So, what you do is you take 3 of these things branes, and there is some intersecting brane model or whatever. So, you take 3 of them which gives SU2, 2 of them which gives you a U2. So, you get a U3 U2. You may think U1 Y can come from here, actually no, it turns out you have to put something and they have to intersect in a particular manner to get the fermionic spectrum, which I have not discussed again out here. So, there is a whole what I call technology which has been developed, and even sometimes it is called geometric engineering. There are geometric engineering of field theories, that is what they are called, and it is sort of a very dramatic change in our understanding of not just classical field theory, but quantum field theory. So, I am done.